Chapter 1 introduces some gas concentration units and units that we're going to see as we talk about this whole first unit with gases. It also starts to look at rate laws and calculating rates of decay, and then it looks at temperature dependence as well. So let's start with gas concentration units. We'll start with some units here. So the first one they talked about were a couple of what we call absolute. So absolute is when you're directly comparing how many gas particles you have. So since gases are pretty dispersed and diffuse and not very dense, a lot of times instead of using something like moles, we'll see the actual number of particles. So the first one, the first concentration unit you will see is expressed in number of molecules of whatever it is you're looking at per volume of centimeter cubed. So you're looking at, for example, ozone, the number of ozone molecules that you would have in a cubic centimeter of volume. So this one, a lot of the plots and figures in chapter 1 are using this unit right here. So another one that's an absolute is partial pressure. So the partial pressure we designate as pressure, and then you'll see a subscript like A, where this designates the gas we have. So if this was ozone, this would be P, and then we'd have O3 right here. Okay, so partial pressure, let's kind of take a look at this. So using the ideal gas law, we have P times V equals N, R, and T. Okay, so in a general sample of gas, we can use this. If we're looking at, say, gas component A, this turns into the pressure of A times the volume equals the number of moles of A times R and then times T, where R is our gas constant. Okay, so often we like to express the partial, to get the partial pressure, we like to put N and P together. So N, number of particles, not P, V, N and V together to get something that looks like this, where you have number per volume. So this is our number and this is volume. Okay, so I'm going to divide by volume there. So we'll get the pressure of A is equal to the number of moles of A over the volume multiplied by RT. So moles per volume, that's essentially the concentration of gas A. So oftentimes this is designated as essentially MA times RT. Okay, so the pressure of gas A is essentially the concentration of gas A times RT, where T is the absolute temperature and R is the gas constant. So either one of those two we can use for the partial pressure. Okay, so kind of again, since gases are so dispersed, sometimes these moles would be replaced with number of particles. This could be number of particles per volume times RT. So number of molecules is equal to moles times Avogadro's number, where Avogadro's number is 6.022 times 10 to the 23rd. So just a little refresher on that. Okay, so we can go in between molecules and moles quite easily just by using Avogadro's number. So you'll see that a fair amount where, again, in chemistry, we're used to using moles, but you're going to see moles quite often with gases is going to be separated with the number of particles or number of molecules. Okay, number three, we start getting into relative concentration units. So the first one, we have the mole fraction. So the mole fraction would be moles of A over moles total. Okay, so just again, kind of we use this in Chem 121 when we talked about gases. It's almost like a percent. How many of A in the total amount? And again, this could also be with particles. So molecules of A over total molecules. Okay, so either one of those two, again, when you're looking at parts of the whole thing. And then kind of a slight variety of this, we have specific mole fractions that we talk about where these totals are in terms of a million, a billion, and a trillion. So parts per million is when we have the number of molecules over 10 to the 6 total. So parts per million, the number that you have of whatever it is you're looking at, your solute over a million total. Then we have parts per trillion. So again, your number of molecules over now 10 to the 9. Oh, sorry, that's parts per billion. Parts per billion, skipped one. Million, billion. And then parts per trillion is your number of molecules over now 10 to the 12 total. Okay, so we see these often as well. How many parts in a million you have, how many parts in a billion, or how many parts in a trillion. But again, these kind of just go back to these sort of relative types of ways we express concentration here. So again, all of these, 1, 2, and 3, are all just ways that we're going to express concentration. Okay, so let's do a quick example. So let's look at CH4, methane, which is a gas that is a pollutant in the atmosphere. So let's say there's 1 times 10 to the 11 molecules per centimeter cubed. Okay, so we have 1 times 10 to the 11 molecules per centimeter cubed. So let's convert this, or let's find the partial pressure. What is the pressure of CH4 at negative 10 degrees Celsius? So in the upper atmosphere where it starts to get a little chilly, what is our pressure at negative 10? Okay, so for a partial pressure, so our pressure of CH4 is equal to moles of CH4 over our volume in liters times R and T. Okay, so if we're looking for pressure in atmospheres, since our gas constant R is in liter atmosphere per mole Kelvin, and to get things to sort of cancel out the way we need to have the proper units here. So this is just going to start off with a unit conversion. So we have 1 times 10 to the 11 molecules per centimeter cubed. Okay, so to get our units to cancel with the gas constant unit of R, I'm going to need this to be in moles per liter. So again, remember R. So remember our R is 0.0821 liter atmosphere per mole Kelvin. So all of our units need to match up. So moles, liters, Kelvin. Okay, so using Avogadro's number, 1 mole is equal to 6.022 times 10 to the 23rd molecules. Okay, so molecules cancels. And then 1 centimeter cubed is equal to 1 milliliter. So our centimeters cubed cancel. And then finally, 1,000 milliliters is equal to 1 liter. Okay, so if we punch this into our calculators, okay, so we have 1 times 10 to the 11 We're going to divide that by Avogadro's number. Okay, so that's our first step. Multiply by 1, divide by 1, okay, then times 1,000. So we get 1.66 times 10 to the minus 10 moles per liter. Okay, so now that we have our concentration units there, now we can plug this back into find our pressure of CH4. So we have 1.66 times 10 to the minus 10 moles per liter times R, 0.821 liter atmosphere per mole Kelvin times our temperature in Kelvin, which is 263 Kelvin. So if we look, moles cancels, liters cancels, and Kelvin cancel. So I punched this in my calculator. I got 1.15 times 10 to the minus 5 atmospheres. So that is our pressure of CH4. Okay, so this is a fairly small number. Again, remember atmospheric pressure down in the troposphere where we're at, or sort of normal gases, is 1 atmosphere. So up here where the CH4 is at these concentrations, the partial pressure is pretty low. So that's a lot of times why gases, this is sort of the more preferred unit, because that's such a much larger number than dealing with such small pressures like you see here. Okay, so next section, we're going to look at energy and enthalpy. So let's look at energy from light. So energy is equal to h nu, which is also equal to hc over lambda. So Planck's constant times frequency, or Planck's constant times the speed of light divided by wavelength. So our constants here, c, the speed of light, 3.00 times 10 to the 8 meters per second, and Planck's constant, 6.626 times 10 to the minus 34 joule seconds. Okay, so this is energy, when we're looking at energy from light, either expressed as frequency or in terms of wavelength. Okay, so frequency, the units of frequency are seconds minus 1 or hertz, and typical units of wavelength for lambda, meters are SI units there. Okay, but we're going to see that a lot of times when we're dealing with atmosphere and gases and light, most of our wavelengths of light are in the visible and the ultraviolet, and these ones are measured in nanometers. So there's a sort of expression where we can kind of take H and C, and instead of having it in terms of meters, if we put it in terms of nanometers, we get the HC in nanometers as 119,627 kilojoules nanometers per mole. Okay, where we did a couple of things here. Again, generally energy for a process, and especially like a reaction, is in kilojoules. So joules going to kilojoules instead of having meters, meters going to nanometers. And then energy is usually expressed in kilojoules per mole. Okay, so we're going to you're going to use this variety of it more. So if you need the energy of a particular process, it's just our Planck's constant in the nanometer version, and then divided by the wavelength now in nanometers. Our nanometers will cancel, and then we'll get kilojoules per mole. So how much energy it takes for a whole mole of, for example, a gas. Where in these ones here, you would get the energy in terms of 1 photon of light, so 1 energy packet. Here we've scaled it up to a whole entire mole of energy. Okay, so either one of these is useful depending on what you're doing here. Okay, so here for just a particular wavelength or photon. Here, if you're talking about a process larger scale, again, in terms of moles and things like that. Okay, so one next thing. We're going to also look a little bit at enthalpy. So enthalpy is the energy change associated with a process. So enthalpy, there's one we use for formation reactions. So the formation of the products subtract the sum of the formation of the reactants. Okay, so the energy of the products minus the energy of the reactants gives you the energy change of a process. So this process could be a chemical reaction. It could be like what we're going to talk about in here, where a photon of energy of light comes in and breaks a chemical bond. Any sort of process, the energy, sum of the energy of all of the products subtract the energy of the reactants gives you the overall energy change in terms of enthalpy. So delta HF naught is the standard enthalpy of formation. Okay, so this is something that is looked up in a table. Okay, so we also can express the enthalpy of a process. Essentially comes down to looking at bond breaking and forming. So bonds breaking, so what's happening on the reactant side? Subtract the energy of bonds forming, which happens on the product side. So you can approximate the enthalpy change of a process by looking at the energy that is used to break bonds and the energy that is released to form new bonds. So the difference in those can give you the enthalpy of a reaction also. So we do use both of these two methods to get the enthalpy of a reaction or a process. Okay, let's look at an example here. So if we look at the reaction of ozone decomposing to oxygen molecule plus atomic oxygen, the enthalpy of that process is positive 105 kilojoules per mole. Okay, so 105 kilojoules per mole. Okay, so if we kind of take a look at this process here, about what's happening. So oxygen, or ozone, excuse me, is 3 oxygens. So if we looked at the Lewis structure for ozone, we get this here. We have a central oxygen with 1 lone pair, double bonded to an oxygen with 2 lone pair, and single bonded to an oxygen with 3 lone pair here. So in this process, what's happening is we're breaking one of these oxygen bonds to form oxygen molecule and atomic oxygen. Okay, so double bonds are much more difficult to break. So this is the bond that's broken right here. So for this reaction, we can kind of say that what is happening here is this bond is breaking. So this overall change in energy is coming from breaking this bond. So it requires energy to break bonds, which is why it's positive. So really the only thing that's happening here is this bond is being broken. Okay, so when that happens, we get molecular oxygen and we get atomic oxygen. Okay, those are our 2 products. So again, the enthalpy we could calculate this way. If we looked up the energy required to sort of break this bond, we could sort of get there that way. Okay, so let's find what wavelength of energy would we need to have this reaction go to completion here. So what is the wavelength of light required? Okay, so we want to know the wavelength of light required to break that bond there. Okay. So let's use, since we have our delta H in kilojoules per mole, we can use this form of the equation. So we have E equals 119,627 kilojoules nanometers per mole over the wavelength in nanometers. Okay, so they've given us our energy. That is the 105 kilojoules per mole. We're going to set that equal to 119,627 kilojoules nanometers per mole over wavelength. And we're going to solve now for the wavelength of light required for this. So the wavelength is equal to 119,627 kilojoules nanometers per mole divided by 105 kilojoules per mole. Okay, so if we put this in our calculators, 119,627 divided by 105, we get 1,139. So this would be the wavelength of light that would be required to break this bond right here. Okay, so not very much. This bond doesn't have very much energy. Okay, so again, I kind of mentioned that reactions happen from bonds forming and bonds breaking. So if we were to look at this, if we look up the bond energy of an oxygen-oxygen single and an oxygen-oxygen double, we get the following. So oxygen-oxygen single is 146 kilojoules per mole, and an oxygen-oxygen double is 498.4 kilojoules per mole. Okay, so this is not that different from this here. The only thing that might be different is, say, states, or again, this one here, a little bit different because it has the double bond here on the other side. And also there's resonance structures going on here as well. So that's why we get kind of the difference here. If it was more of a true oxygen-oxygen single, we'd probably be closer to this. But again, because there is resonance structures here, that's why we're getting sort of a difference. But these two are fairly similar, a lot different than, say, what we see here. So if we were to calculate this one, the energy it takes to break the double bond. So if we look at the energy that would be needed to break that double bond, we'd have our 119,627 divided by our energy of that bond, our 498.4. So the energy that it takes to break that oxygen-oxygen double bond is more like 200, or excuse me, the wavelength is more like 240 nanometers. Okay, so this one, a lot more energetic, would take a lot more energy to break that bond. Okay, so that's how kind of using these formulas right here work. Allows you to look at the energy required for a particular process. If you know the energy, you can calculate essentially a wavelength that you would need for that. Okay, so our last piece here, we're going to look at kinetics. So the last part of the chapter, we're going to look at kinetics and rates. Okay, so when we look at a reaction over time, so as time passes and we look at the concentration in whatever units we're using, most reactions or in reactions, we see a decrease in concentration over time. So as a reaction proceeds, the concentration decreases over time. So it decreases really rapidly at first and slowly at the end. So if we look at the rate of the reaction, also the rate decreases over time as the concentration decreases. Okay, so as we decrease the concentration of gases, the rate also decreases. So we can find the rate of a reaction by taking the change in concentration over the change in time. So when we talk about the rate, we're talking about how the concentration changes over a particular unit of time. Okay. So another thing to kind of note, reactions occur due to collisions. So in order for a particular reaction to occur, reactant A has to collide with reactant B to break bonds and form new bonds and things like that. So as you have lots and lots of A and B colliding all over the place, the reaction happens fast. But over time, as the concentrations of A and B are decreasing, A is colliding with B a lot less, so the rate decreases. So also, we'll see some reactions are more dependent on concentration. Okay, so the rate is dependent not only on, again, concentration, but some are dependent even more. So we call this order. So order is essentially the degree in which the reaction is dependent on one of the reactants or more. So let's say we have the general reaction of A going to products. Okay, so our rate would be equal to the change in concentration of A over the change in time. So the most common rate orders we see is something called first order. So if A is first order, the rate is proportional to the concentration of A to the first power. Okay? Which would mean, say, for example, if you doubled the concentration of A, you would double the rate. Or if you triple this, you triple this. So whatever happens to A essentially happens to the rate. Things that are more dependent have higher order. So we have something called second order. And in this one, the rate is proportional to the concentration of A now squared. So if you were to double A, this would increase by a factor of 4. Okay? Or if you were to triple this, this would be a factor of 27. Okay? So, is that right? No, I was just kidding. That was 9. If this is tripled, then this would be 9 times as fast. I'm sorry, I went third order. Okay, so this, something that is second order, has a larger dependence on the rate. Okay, so when we want to change this proportion and solve for like, hey, if I do know the concentration of A, what then would be the rate? We get what's called a rate law. So a rate law is written as the rate is equal to K, the rate constant, times the concentration raised to some power of N, where generally N is either first or second order. Doesn't have to be. It could be something like a half order or a third order, but 1 and 2 are the most common that we're going to see. Okay, so let's consider the reaction of A plus B producing products C. So if this is first order in A and B, which is the most common, we would get that rate is equal to K times the concentration of A times the concentration of B. Again, where A and B are first order. Okay, so that would be our rate law. Rate is equal to KAB. So the way the rate law works is if we know the constant and we know initial concentrations of A and B, we can calculate what the rate would be, or again, how A and B are disappearing over time or how C is forming over time. So for example, if the concentration of A equals 3.0 times 10 to the 5th molecules per centimeter cubed, and the concentration of B equals 1.0 times 10 to the 6 molecules per centimeter cubed with a rate constant equal to 1.5 times 10 to the minus 5 molecules per centimeter cubed second. What is the initial rate? Okay, so when we're doing this, we're calculating what's called initial rates. We have our starting concentration. So this is the rate at which the reaction is going to start. Again, that doesn't mean towards the end of the reaction it's still occurring at that rate. It's just what's sort of the starting rate for that particular reaction. Okay, so to solve, we'll set up our rate law. So the rate is equal to our K 1.5 times 10 to the minus 5 molecules per centimeter cubed second times our concentration of A, 3 times 10 to the 5 molecules per centimeter cubed times B, 1.0 times 10 to the 6 molecules per centimeter cubed. Okay, so this is our rate law, K, concentration A, concentration B, where they told us it was first order. So I'm going to put the ones here, even though we don't really need to, just to remind us this is first order. Okay, so just multiply through here. And the initial rate is 4.5 times 10 to the 6 molecules per centimeter cubed second. So that means that in a centimeter cube of area, we have 4.5 times 10 to the 6 molecules disappearing per second for A and B. So when they react, 4.5 times 10 to the 6 molecules per second of time are disappearing for A and B, which also means we're producing 4.5 times 10 to the 6 molecules per second in that centimeter cubed of area for the product C. Okay, so that's how rate laws are used. Again, where we're looking at if it's a reactant, how the reactants are disappearing over time, so how they're disappearing over time, and if it's a product, it would be how they are forming or being produced over time. Okay, so the last thing we want to look at with rate is the temperature dependence. So reaction rates are temperature dependent, which is important because we did learn from sort of the first lecture in chapter 1 that as we move through the atmosphere, we get a lot of changes in temperature. And in fact, our layers of the atmosphere are kind of defined according to temperature increases and decreases as we move up in altitude. So we do know that there are sort of a lot of fluctuations in temperature. So the rates of reactions change based off of temperature. So reactions are due to collisions. So the higher the temperature, the higher the rate constant K, which equals faster reaction. So at higher temperatures, reactions happen faster. And not even just a little bit, this is an exponential. So if we look at temperature and K, we have an exponential increase in K with temperature, where we can say K is equal to A E to the negative EA over RT. Okay, so what sorts of things do we have here? K is the rate constant. A is a collision, or what we call frequency factor. R is the energy gas constant, or 8.314 joules per mole Kelvin, and T is the temperature in Kelvin, with EA being our activation energy. So remember for what activation energy is, if we look at an energy profile, something like this, where we have our reactants and our products, this initial sort of energy hump that we have to overcome for a reaction to proceed is called the activation energy, EA. Okay, so this energy threshold, and this comes from our particles having enough energy to collide and break bonds. So we have to be able to break initial bonds with collisions, and that's where activation energy comes from. So we also see this in a what we call linear form. So this is great, but it turns out that A is kind of hard to measure. So we'd like to turn this into a form that doesn't involve A. And to do that, we turn this into the natural log of K versus 1 over T, where we have the natural log of K equals negative EA over R times 1 over T plus the natural log of A. So, and when we do this, the plot looks linear. Okay, so for this way, we can find why this is useful, because the slope of this line is equal to negative EA over R. So if you can graph the natural log of K and 1 over T, you can get the activation energy of a particular reaction, and thus essentially eliminating that frequency factor or collision factor A, which is so difficult to measure. Okay, so oftentimes we do this one here because, again, we can separate this out where activation energy over R is just equal to our slope. And finally, with this, we also have what's called the 2-point Arrhenius equation. So the 2-point Arrhenius equation kind of takes the slope and puts it together. So we'll see this one quite a bit. Okay, so if you have your two rate constants and your temperatures, we've eliminated A completely by combining essentially the slope into one sort of giant expression. And this one is used kind of the most because, again, you don't have to rely on that collision factor A, which is so difficult to measure. Okay, so for example, let's look at the 2-point. So at negative 15 degrees Celsius, the rate constant K is 4.5 times 10 to the minus 5 seconds minus 1, with an activation energy of 23 kilojoules per mole. So I want to know what is K at 20 degrees Celsius. Okay, so if we know the activation energy, we do know R, we know our two temperatures, and we know one of our Ks, we can solve for the other one. So we have the natural log of K2 divided by our K1, which was 4.5 times 10 to the negative 5 seconds minus 1 equals negative 23 times 10 to the third joules per mole, where I've taken kilojoules and turned it into joules because our R is 8.314 joules per mole Kelvin. So now joules is the same as joules, mole is mole, and we're going to get our Kelvin right here. So this is 1 over 293, subtract 1 over 258. Okay. So now we've filled in all of the values given to us in the problem, turning our temperatures into Kelvin. Now we can solve for our K2. So I'm going to condense all of this down. All of this condenses down. We have natural log of of K2 over 4.5 times 10 to the minus 5 seconds minus 1 equals 1.281. If I take this divided by this, multiplied by the difference of that. So now we want to take the anti-natural log. So we're going to take e to the both sides, which gets rid of this. So we get k2 over 4.5 times 10 to the minus 5 equals e 1.281. Okay, now it's just solving. So k2 is 1.6 times 10 to the minus 4. Okay, so our temperature went up and our k2 went up. Okay, so you don't have to use this one all the time. There's an example in the book where they did use the sort of standard Arrhenius equation here, where they gave you A and they asked you for a particular K or T to just solve this. So if A is available, you can use this one here. If A is not available, then oftentimes we use this form of the activation energy there. Okay, we're again to note that our temperature went up and our K went from 4.5 times 10 to the minus 5 to 1.6 times 10 to the minus 4, so it increased as well.